Okay, so welcome back to the last section of Chapter 5, Section 5.5. Last time we talked about what I was calling the Substitution Rule. And so far, I've sort of shown by example. I haven't stated exactly what the Substitution Rule is. But it's this idea of a change of variables. But there is a more concrete statement of the substitution rule. I'll just state for completeness. If u equals g of x is differentiable, so for a change of variables, if you can take the derivative, whose range, or possible y values, is an interval I, and f is continuous on I, then the indefinite integral of f of g of x, g prime of x, dx, equals the integral f of u du. It's basically, in symbols, the same thing as what we were doing, just this is a more exact statement. Now, and you can think of this as the chain rule for integration. Now, how does that apply to the definite integral? Well, if I take a definite integral, I have from a to b of same setup, f of g of x, g prime of x, dx. That's going to be the same as g of a, g of b, f of u, du. Now that's still in pretty abstract symbols. What does that mean? So, what it basically means is, well, inside the integral, this part is the same as what I did before. But when I look at the limits of integration, the little numbers that I'm using to plug in, those are changing based off of my substitution. So let's just do an example to illustrate what this is talking about here. Let's take the integral from 0 to 3 of dx over 5x plus 1. Now this is a fraction, so typically a good change of variables is going to be your denominator. So then my du over dx is going to be what? It's going to be 5. So in other words, dx is du over 5. So I can plug it in. I'm going to leave these blank for now, but we'll fill those in shortly. You'll have du over 5 and then over u. Now what does the substitution rule say goes in here? Well, it says take your normal limits of integration and plug them in to your change of variables. So for the first one, it would be u equals 5 times 0 plus 1, or 1. For the second one, it's u equals 5 times 3 plus 1, or 16. So, in other words, what we have, just going to clear some space, is this is the integral from 1 to 16 of du over 5u. And so we just have to find what that integral is. Well, we can pull out the 5, 1/5, because that's a constant. 1/6 du over u, or the integral of 1 over u du is the natural log of the absolute value, so this is 1/5 natural log of the absolute value of u evaluated from 1 to 6. And now we can just plug in. And what do we get? Or sorry, not the 6. 16. And what do we get once we plug in? Well, this is going to be 1/5 natural log of 16 minus 1/5 natural log of 1, which is 0. So it's 1/5 natural log of 16, which is a number. And that is how doing definite integration with u sub works. There's only that one extra step of change your limits of integration. So let's just do a couple examples. 0 to the 2, x minus 1, e to the x minus 1 quantity squared dx. Well, there's an exponential, so there's a pretty good bet that my u will be whatever the exponent is. Okay, so let's take the derivative. What do we get? du over dx. That's going to be, by the chain rule, 2x minus 1 times 1. In other words, dx will be, by solving, du over 2x minus 1. And we get that by, we have that du is 2x minus 1 dx, so we divide this term by both sides, and we get du over 2x minus 1 equals dx. So let's plug this in. It will be x minus 1 e to the u, right, because that's why I chose that particular change of variables, times du over 2x minus 1. These cancel. And we still have our limits of integration. All I do is I plug in these numbers into my change of variables. 0 minus 1 quantity squared is 1. 2 minus 1 quantity squared is 1. And so we have to integrate this thing. Now you could integrate this, and what are you going to get? 1/2 e to the u evaluated from 1 to 1, or 1/2 e to the 1 minus 1/2 e to the 1, or 0. And that is another example. Okay, so let's look at one more example. One to 2 e to the 1 over x divided by x squared dx. Now this one's a little tricky because you have something in the denominator, so that makes you want to choose that to be your substitution, but you also have an exponent. So you could try one. I'm going to try the exponent. What is du then? Well, it's du over dx is negative 1 over x squared So du is negative dx over x squared, or dx is negative x squared du. So let's plug this in. What do we get? Well, to get our limits of integration, remember we plug it into our change of variables. This will be 1/2 and 1. And then there's e to the u over x squared times our dx is negative x squared du. X squareds cancel, and look at that. It works out. So what do we get? Negative pulls out. This is negative 1 to 1/2 e to the u du. Or negative e to the u evaluated from 1 to 1/2. Negative e to the 1/2 minus negative e to the 1, which is going to give you a number. And that's how the substitution rule works. Now, a little something on the bookend. Another property that is mentioned in this section that you can use substitution rule to show that it works is properties about even and odd functions. That they use substitution rule to prove, which is why they lump it into this section. We're not going to do that. I'm just going to give them to you. I will never require you to use them, but if you know them, they might be handy. If f is even, an even function, then the integral from negative a to a, f of x dx, is 2 times the integral from 0 to a, f of x dx. And before we look at the second one about odd functions, let's see why this is true. Well, if you have an even function, its behavior on the left is the same as its behavior on the right. So to do it once and to count it twice is the same as to do the other side, right? Because both sides are the same thing. So since both sides are the same thing, you could just do the one side and add it again. Now, if f is odd, then the integral from negative a to a, f of x dx, is always 0. Now this just follows because if you remember, if I have an odd function doing something up here, on the negative axis it's doing the same thing, but below the x-axis. So whenever you sum up their areas, they cancel each other out because they're doing opposite. They're doing the same thing on the opposite sides of the axis. Okay, so, and the examples of these that you could envision is, to give you an example, f of x equals cosine x, and f of x equals sine x, both on negative pi over 2 to pi over 2. And you can check that it does work out. But that is never a property I'm going to force you to use on anything. But if they're ones that you naturally see that this is even or this is odd, then you can use them. So that's it for Chapter 5. There is 2 sections of Chapter 6 that we will discuss. But just, but before that, we do have our little thing for Exam 4, our mini projects. So don't forget about those. Those are due soon. And I will see you on Canvas pretty soon, but on YouTube won't see you for a couple days.